Some of you watching this will live to be thousands of years old. If you want to, and if we as scientists can develop new technology that can determine where every single atom is within inside of a human cell. What do I mean by that? Here's a simple chemical compound. In white are hydrogen atoms, carbon atoms in black, nitrogen atom in yellow, and 2 oxygen atoms in red. We want to make new technology that can determine the exact structure of every compound inside of your cell and also how the compounds move in time. If we can do that, then we can design new drugs that target only the proteins that we want to bind to and don't bind to any of the proteins that we don't, which would give you toxic side effects. For example, in our laboratory, we're participating in a cure for HIV/AIDS. HIV is really tricky. Although you can take a combination of medicine that knocks out the active virus and you can live for a long time if you have HIV, 1 in a million of your cells harbors a latent, hiding, sleeping viral DNA. Now this viral DNA will be translated and transcribed into virions if you stop taking the medicine even for a couple weeks. So we want to make a new combination of compounds that activate these latent HIV reservoirs so they can be targeted and destroyed. But when you take the new compounds, you only want these compounds to turn on the hiding HIV reservoirs and not to turn on other pathways in your cells that could make you sick or give you toxic side effects. So that's why we have to know where every single atom is, so we can make a new medicine that binds only to the proteins that we want. Now the key to this new technology to determine these structures is to increase the signal of magnetic resonance. You're familiar with magnetic resonance from MRIs, or magnetic resonance imaging scanning in a hospital. Now we use the same kind of technology, except down at an atomic scale to determine the structure of very small compounds. To improve the signal to noise, which is the key in these experiments, we use microwaves. Now the microwaves that we use are 20 times higher frequency than what you use in your microwave oven at home. And you can't buy a microwave source that makes the microwaves we need, so we design our own. These are the engineering schematics of one of the gyrotrons, or microwave devices that we build in our group. Also important in our experiments is that we cool our samples very cold, colder than space, all the way down to 4.2 Kelvin using liquid helium. That's only 4 degrees above absolute zero. Now, helium is really expensive, and so we want to be really efficient with the liquid helium. And also in our experiments, we have to spin our samples mechanically very fast. This spinning boosts our signal intensity and gives us really clear signals. And the faster you can spin, the better. Right now, we can spin our samples at about 10,000 times per second. That's 10,000 rotations per second, not RPMs. And ultimately, we want new technology that can spin our samples at 1,000,000 times per second. This would really boost our signal strength and allow us to determine these structures of drugs and proteins within intact human cells. The key to our technology is to use a new spherical container for our samples. Rather than using cylinders like everybody in our field has done for the last 60 years, we were inspired by nature. You know, what in nature spins really fast? The Earth, the sun, a pulsar. So now we're using spheres instead of cylinders. Here's a 9.5 millimeter sphere, and we put it inside of a 3D printed stator. It only costs about 35 cents to make this stator, and we've made a few hundred of them. And then just with the air from this compressed can, I can spin our new spherical rotors. You can hear the spinning. These spheres and this new technology for magnetic resonance is going to be very important for medicine in the future. Thank you.